magnitude and logarithmic models. Now, in this video today, and in this lesson, we're going to talk about models of logarithms. Now, when comparing quantities, their sizes sometimes span a wide range. This is why scientific notation was developed. For instance, the planet Mercury is 57.9 billion meters from the sun, whereas Pluto is 5,900 billion meters from the sun, roughly 100 times further. In scientific notation, Mercury is 5.79 times 10 to the 10th meters from the sun. Pluto is 5.9 times 10 to the 12th meters from the sun. So Pluto's distance is 2 powers of 10 greater than Mercury's distance. The common logarithm of the positive quantity is its order of magnitude. So we say Pluto's distance from the sun is 2 orders of magnitude greater than Mercury's. So if we look here, 10 to the 12th is 2 orders of magnitude, or 10 to the second power, greater than that of Mercury. Now, orders of magnitude can be used to compare any like quantities. A kilometer is 3 orders of magnitude longer than a meter. A dollar is 2 orders of magnitude greater than a penny. A horse weighing 400 kilograms is 4 orders of magnitude heavier than a mouse weighing 40 grams. And then New York City, with 8 million people, is 6 orders of magnitude bigger than Earmuff Junction, with a population of 8. Now, my guess is that Earmuff Junction is somewhere up in Alaska. I have been yet to find it. I've looked for it on Google Earth, and I've Google searched it, and I've never found it. So it could be. I'm thinking it's not a real place. They're just using it for comparison's sake. Okay? Now, what I'd like you to do, I'd like you guys to work on exploration 1 at this time. So using a calculator, compute log of 4 times 10, log of 4 times 10 to the second, log of 4 times 10 to the third, all the way times log of 4 times 10 to the 10th. Then answer the questions. What's the pattern in the integer parts of these numbers? What's the pattern of decimal parts? How many orders of magnitude is greater? So what was the log of 4 times 10? Log of 4 times 10? 1.6021. How about the log of 4 times 10 squared?
2.6.
How about the log of 4 times 10 to the third?
2.6.
Start writing that again. And then this one will be 10.6021. So, what is the pattern in the integer parts of these numbers? Integer parts. So it's saying 1, 2, 3. So there's increasing of 1 for every increase in power of 10. So I can probably safely say log of 4 times 10 to the 100th power will be 100.6021, right? Yep. Now, what is the pattern of the decimal parts? Drew. Okay, they're exactly the same. Now, this part you guys might not get. That's okay. How many orders of magnitude is greater is 4 times 10 to the 10th than 4 times 10? 9. 10 minus 1 is 9. So 9 orders of magnitude greater. Now, orders of magnitude of many applications. For a sound or noise, the bell mentioned in section 3.3 measures the order of magnitude of its intensity compared to the threshold of hearing. For instance, the sound of 3 bells or 30 decibels has a sound intensity 3 orders of magnitude over the threshold of hearing. Now, orders of magnitude are also used to compare the severity of earthquakes and the acidity of chemical solutions. So the next 2 examples we'll be talking about earthquakes and acidity of solutions. Now, we are going to be using this formula for example 5. Now, as mentioned in exercise 52 of 3.4, which even though we weren't assigned that, it was mentioned there, the Richter scale magnitude R of an earthquake is R is equal to log of A divided by T plus B, where A is the amplitude in micrometers, the vertical ground motion at the receiving station. So what they're talking about is how much the ground moves up and down. T is the period of the associated seismic wave in seconds. We're talking about period of waves once we get to the trig section, so chapter 4 and chapter 5. And B accounts for the weakening of the seismic wave with increasing distance from the epicenter of the earthquake. So if you think about it, you guys have seen earthquakes on the news, right? How are they depicted on the news?
The magnitude.
Okay, so it finds epicenter, and then what's coming out after it?
Rings of vibration.
Rings, right? Basically, circles are coming out after it to see how far it's being felt out. That's what the B is. Okay? Now, in example 5. Example 5A will have a heck of a lot more algebraic work than 5B will. Let's hope that you guys can figure that out. How many times more severe was the 2001 earthquake in India, which had a Richter scale of 7.9, than the 99 earthquake in Athens, which had a Richter scale of 5.9? So what we're going to do here, R1 will be, what's our formula? It says log of A over T, so log, I'm going to say A1 over T plus B. That'll be 7.9. R2 will be log of A2 divided by T plus B. That will be 5.9. What we're going to want to do here, we're going to want to take R1 minus R2, which will be log of A1 over T plus B minus log of A2 over T plus B, and that will be 7.9 minus 5.9. Now we're going back to section 3.4 here when we are subtracting these two logarithms, right? So when we're subtracting the two logarithms, we're going to divide. So what we can have then, it'll be log. We'll take that back. Before we do that, let's do this. What happens to our B values? These will cancel out, right? So we'll divide this. Equals this, correct? So you understand why the B's cancel out? Yep. Okay. What happens to the T values? Why are the T's going to cancel out? When they're both in the denominator like that, they'll just simply cancel out. Because remember, when you divide by a fraction, you're multiplying by the reciprocal, so they'll cancel out. So really, I'll be left with log of A1 divided by A2 is equal to 2. Now, what's the base on that log right now? The base is 10 because we can't see it. So really, I'll have A1 over A2 is equal to 10 squared. 10 squared is equal to how much? 100. So this will be 100 times greater. So the earthquake in India, which had a Richter scale measurement of 7.9, was 100 times greater in magnitude than the one in Athens. Now, I want you guys to work on B.
You don't do anything like this.
Now, how many times more severe was the 95 Kobe, Japan earthquake, which had a Richter scale of 7.2, than the 94 Los Angeles earthquake, which had a Richter scale value of 6.6? Well, do we have to do all this crazy mathematics here? No, we could start off with this. Log of A1 over A2 is equal to 7.2 minus 6.6. That means A1 over A2 will be 10 to the 0.6 power. 10 to the 0.6 power is how much? 3.98 times greater. Are there any questions on that? All right, moving on. Now, in chemistry, how many people are in chemistry right now? Okay, love that class. The acidity of a water-based solution is measured by the concentration of hydrogen ions in the solution in moles per liter. The hydrogen ion concentration is written as H plus with the brackets around it. Because such concentrations usually involve negative powers of 10, negative orders of magnitude are used to compare acidity levels. The measure of acidity used is pH, the opposite of the common log of the hydrogen ion concentration. So this is what we're going to do here. Okay, this is the formula we're going to use. Just like we used the formula with the log in the Richter scale 1, we're going to be using the same thing here. Now, in example 6, some especially sour vinegar has a pH of 2.4, and a box of leg and sickle baking soda has a pH of 8.4. What are their hydrogen ion concentrations? So for vinegar, okay, for vinegar, what we're going to do, we're going to use that formula. Negative log of H plus is 2.4, which means log of H plus is negative 2.4. What's the base on this then? 10. So that means H plus would be 10 to the negative 2.4. 10 to the negative 2.4, we do need to figure out in our calculators. We have about 0.00398, or 3.98 times 10 to the negative third. Now, if we use the baking soda, again, we'll have negative log of H plus equals 8.4 pH.
The bite breaking of the soda.
Now, what does H plus equal then? I'm going to see if you guys can make the jump mathematically. What does H plus equal? The hydrogen ion.
10 to the negative 8.4.
10 to the negative 8.4. Now, if we put 10 to the negative 8.4 in our calculator, we have 3.98 times 10 to the negative 9. Okay. Now, in part B, we're actually going to use the 10 with the powers for our answer here to get it. Are there any questions how I came up with these answers at all? All right. Now in B, how many times greater is the hydrogen ion concentration of the vinegar than that of the baking soda? All right. So what we're going to do here, we're going to take the vinegar over the baking soda. Now remember, we have a negative exponent in the bottom. We can move it to the top. Or we can take negative 2.4 minus a negative 8.4, which would be negative 2.4 plus 8.4, which is really positive 6. Good. 10 to the 6. That's how many times greater it is. Now in part C, it says by how many orders of magnitude do the concentrations differ? Well, that is just going to be our exponent here, 6 orders of magnitude. Okay? 6 orders of magnitude. Now we can also see that 6 orders of magnitude here. 10 to the negative third is 6 orders of magnitude greater than 10 to the negative 9. Same thing here. 2.4 and 8.4. Okay? Now, I'd like you all to try B and work on B. Okay. The pH of carbonated water is 3.9. The pH of household ammonia is 11.9. What are their hydrogen ion concentrations? So if I have water, I'm going to have H plus will be what? 10 to the negative 3.9.
Oh, yeah.
And then the ammonia,
10 to the negative 11.
now for part B, how many times greater is the hydrogen ion concentration? Well, if we divide the water by the ammonia, we're going to get 10 to the 8th power greater. And by how many orders of magnitude do the concentrations differ? That will be 8. Are there any questions on the chemistry ones or the Richter scale problems? Any questions at all? Object that has been heated will cool to the temperature of the medium which it is placed, such as the surrounding air or water. The temperature T of the object at time T can be modeled by this equation. T at time T will be the temperature of the medium plus the temperature of the initial temperature minus the temperature of the medium, e to the negative kT. Now I want you to think about it like this. That doesn't really make sense. How many people in here drink coffee on a pretty regular basis? Okay. Now, if you think about it, I've got a Keurig machine at home, right? I can set the temperature on my machine. I set it 192 degrees Fahrenheit. My house in the morning, we keep it at 65 degrees Fahrenheit in the morning. Okay? So if you think about it, my initial temperature is 192 degrees Fahrenheit. Temperature of my medium is the air in the house, which is 65 degrees. Does that make sense? Yes, I keep it that chilly in the morning. Okay? Now, what's going to eventually happen is the temperature of my coffee over a period of time will come down to 65 degrees. Does that make sense? That's what Newton's law of cooling is telling us. It's going to tell us the exact time once we get there. Okay? But first, it's going to be a two-part equation. It's going to be a two-part equation. Now, example 7, applying Newton's law of cooling. A hard-boiled egg at temperature 96 degrees Celsius is placed in 16 degrees Celsius water to cool. 4 minutes later, the temperature of the egg is 45 degrees Celsius. Use Newton's law of cooling to determine when the egg will be 20 degrees Celsius. So what we have to do here, we have to look back up here. We have to figure out the temperature of time t, temperature of the medium, temperature of the original, temperature of the medium, and then K and T. We're given all of these, and we'll actually go through it. What would the 96 degrees Celsius be?
Yeah. Initial temperature.
This is the initial temperature, so this would be T sub 0. How about the 16 degrees Celsius? This would be T sub m. Temperature of the medium. 4 minutes later, that will be our T, right? Because after 4 minutes, that's the temperature. And then the temperature at time T will be 45 degrees. So what variable didn't we come up with up here? K. So what we have to come up with is K. Once we find K, we're going to put that back in with the new temperature at time T to find T. So it's going to be a two-step process. So what we're going to have, the temperature at time T is 45 degrees. Temperature of the medium is 16 plus temperature of the original minus the temperature of the medium, e to the negative k times 4 because that is T. What we need to do, subtract 16 from both sides, right? 45 minus 16 is how much? 29 equals 80 e to the negative 4k. just because it's easier to say 4k instead of k times 4. Now, I need to divide both sides by 80. Now, what's the inverse of E? Natural log. So take the natural log of both sides. We should be able to solve for k pretty easily, right? We're going to find the natural log of 29 divided by 80. Divide that by -4. Now, I'm going to do it kind of separate here, just so you can see that it will be positive. So log of 29 divided by 80 is here. Divide that by -4. It's here. So k will be 0.2537. We're not done yet because we have to find t. This will be our new time t. This here, 20 degrees Celsius, will be my new time t. So we're going to put that back in. 20 is equal to 16 plus 96 minus 16 e to negative 0.2537 t. I'll give you a minute to write that down. But again, it's going to be the same solving process. So what's the first thing I have to do? Subtract 16. Then what do we have to do? Divide by 80. Then what? Take the natural log of both sides. Now, if you know, did you notice that I didn't reduce 4 over 80? Do I have to reduce it? No. Could you reduce it? Sure, but you don't have to. Now, to solve for t, I'm going to divide by negative 0.2537. Oops. 11.81 minutes. No, I've never done it myself, but this is something you can do. All right. Now I'm going to have you guys work on B. All right, when we do this, a cup of coffee is cooled from 92 degrees to 50 degrees Celsius after 12 minutes in a room at 22 degrees Celsius. So what is the 92?
Oh, I got it.
This is the initial temperature. The 50 is the temperature at time t. 12 is t. And the 22 is the temperature of the medium. So we put this in. We'll have 50 is equal to 22 plus 92 minus 22 e to the negative 12k. Subtracting 22 from both sides, we'll have 28 is equal to 70 e to the negative 12k. I'm going to take some mathematical liberties here. And I'm going to divide by 70 and take the natural log of both sides just to save time. Okay. That'll get rid of the e and dividing in one step there. If we do this, ln of 28 divided by 70, divide that by negative 12, you get 0.0764. So there's your K value. Now, this 30 will be your new temperature at time T, right? So we want to make that 30 is equal to 22 plus 92 minus 22 e to the 0.0764 t. We're going to subtract 22. So that will be 8 equals 70 e to the 0.0764 t. Again, I'm going to take some algebraic liberties and just kind of combine steps. Oh, it should be negative here, sorry. Okay, this should all be negative. So take this and divide it. Oops. So you should get 28.39 minutes. Okay. Now, there are many, there's not too many of these in the homework tonight, but they will show up again and again, possibly on a test, which will be next Friday. Okay. Are there any questions right now over example 7?